Okay, let's get into this. We're looking at a claim today that I have to say, it feels like physics is just messing with us.
It really does.
The idea is that you can take liquid water under very specific conditions and make it freeze solid by adding heat.
Yeah,
That just completely flies in the face of what we learn in school,
it
right?
absolutely does. I mean, you add heat, things melt or they
Nice.
boil. That's the rule. Our deep dive today confirms this is very real.
So what's our mission here?
Our mission is to unpack this. We need to figure out the exact conditions you need, what's actually happening when that little bit of heat is added, and, what finally triggers this spectacular sudden freeze.
We want to get to that aha moment.
Exactly. That moment where you see how something so stable can become so unstable.
All right, so to even start, we have to talk about the one critical thing you need. It's a phenomenon called supercooling.
Precisely. Supercooling is the absolute foundation for all of this.
So what is it exactly?
It just means the water stays liquid even though its temperature is below its normal freezing point, below 0 degrees Celsius.
So you have liquid water that's technically cold enough to be ice.
Yep. It's in a state where it should be solid by all the rules we know, but it isn't.
How is that possible? I mean, if the molecules are that cold, why don't they just lock into place?
Well, it's a great example of what we call a metastable state. The molecules are sort of suspended. They want to form that nice, neat, crystalline ice structure.
Because that's the lowest energy state for them at that temperature.
Exactly. But they're missing something crucial. They don't have a starting block, what we call a nucleation point.
A nucleation point.
Think of it like a seed. If the water is incredibly pure and the container is perfectly smooth, there are no impurities, no dust, no rough edges for that first little ice crystal to grab onto and start forming.
Ah, okay. So they're all ready to go, but no one has fired the starting gun.
That's a great way to put it. They're effectively trapped as a liquid, just waiting.
So it's like physics has hit the pause button. The water is freezing cold, but its own purity is what's keeping it liquid.
And that fragility is the whole key.
Yeah.
The water is sitting right on the edge of an energy cliff. It just needs a tiny little push.
And that push, that brings us to the really paradoxical part, the trigger.
Right.
Once you have this super unstable, super cooled water, what makes it freeze? Our sources say it can be something as simple as, a touch.
A vibration, a sudden movement.
Or, and this is the one that breaks my brain a little, the simple addition of heat.
And this is where that everyday logic gets inverted. In this very specific state, heat becomes the activation button for freezing.
But hold on a second. If you add energy, you're making the molecules move more, aren't you?
You are.
So shouldn't that kinetic energy make it harder for them to form a rigid crystal? Shouldn't it, if anything, push them more towards melting?
That is the perfect question, and it gets right to the heart of it. You have to distinguish between two different kinds of energy here. There's the total energy of the whole body of water, and then there's the very, very localized energy needed for activation.
So you're saying the bit of heat you add isn't enough to warm up all the water?
Not even close.
Yeah.
It's way too small for that. But it's the perfect amount to affect the individual molecules at a specific point.
Okay, I think I'm following.
The supercooled state is trapped. It's behind what's called an activation energy barrier. The molecules need a very specific local jolt of energy to get over that hump.
So the heat isn't warming the water, it's just shaking it up a little bit.
It's a nudge. It's just a tiny nudge that gives a few molecules just enough of a kick to find their way into that stable crystalline ice formation.
And once they do?
Well, the process of freezing is exothermic. It actually releases a little bit of energy.
Right.
So that first crystal forms, releases energy, and that energy triggers the molecules next to it to crystallize, and so on.
A chain reaction.
A rapid chain reaction,
Oh.
a total systemic collapse of the liquid state.
And it is dramatic. I mean, you see the videos of this, and the water turns to ice in, what, a second?
Less than that sometimes.
Yeah.
It looks like a wave of ice just propagating through the glass. It's
Yeah.
like something out of a science fiction movie.
Just from a single touch.
The analogy of a structural collapse is perfect. Imagine a house of cards, balanced perfectly.
Oh.
A huge gust of wind would just blow them everywhere. That's like adding a lot of heat. But a tiny, precise tap on the bottom card,
The whole thing comes down.
the whole thing instantly falls into a much more stable state flat on the table.
Right.
That little tap was just enough energy to bridge the gap to stability.
That makes so much more sense. The water was already cold and ready. It just needed that tiny nudge to finish the job.
And this isn't just some, cool lab trick,
Hmm?
scientists are actually using this idea in some really critical fields.
Right. So what part?
All right.
So how are researchers using this ability to control the exact moment of freezing?
Well, our sources point to three main areas where this is a really big deal.
And the first one sounds incredibly important. Research into organ storage and cryopreservation.
Yeah, this is probably the most vital application. When you freeze organs or any biological tissue, your biggest enemy is ice crystals
Why is that?
because they're sharp. They expand. As they form, they're like millions of tiny little knives that shred cell membranes. When you thaw the tissue out, it's just destroyed.
Ah.
So researchers are looking at supercooling as a way to get the tissue below freezing without any crystals forming at all, to hold it in that stable liquid state.
So you could potentially store it for longer and with less damage.
Exactly. And understanding that activation barrier lets them control or even prevent freezing until the moment it's needed. It's a game changer.
Wow. Okay. What's the second application?
It's a bit more industrial. Pure ice manufacturing.
Pure ice. I mean, isn't ice just ice? Why do we need it to be ultra pure?
Well, not for your drink. This is for highly specialized scientific work, calibrating very sensitive instruments, for example, or in certain material science experiments.
Where any impurity could throw off the results.
Precisely. By controlling the supercooling and then triggering a very controlled crystallization, you can force out almost all impurities and build a nearly perfect ice lattice, molecule by molecule.
And the third area.
The third is more about fundamental science. It's for studying matter under extreme conditions.
Like what kinds of conditions?
Think about the bottom of the ocean near a deep-sea vent, or inside a planet's core.
Mm.
Conditions of incredible pressure and temperature.
Our normal models of physics probably break down there.
They often do. So studying water at these weird boundary cases, where it's super cold but needs a tiny nudge to change state, gives us a perfect little laboratory. It lets us see how materials and structures change under extreme stress, almost instantaneously.
So this whole deep dive really changes how you think about freezing. It's not just this slow, gradual process of removing heat.
Not at all.
It shows that it can be instant, and it can be triggered by the very thing you'd expect to prevent it. The stability of something as simple as water is. Well, it's way more complicated than it looks.
It really is. It shows that an unstable system can just be sitting there, waiting, and the energy needed to push it over the edge into its true, stable form can be tiny.
Fascinating thought.
And it really makes you wonder, doesn't it? If a simple touch or a bit of warmth can cause such a dramatic instant change in water, what does that say about other things we think of as stable?
You mean other materials?
Materials, systems, anything we consider fixed. It makes you question what hidden potential for collapse or for sudden change is waiting in things all around us, just waiting for the right little nudge.